goal of this lecture? Today I will see uniform boundness theorem and the Boundary category theorem. What is the Boundary category theorem? This is actually consequence of uniform boundness theorem. The theorem is, just recall the Boundary category theorem, because to prove the uniform boundness theorem, this is actually use of Boundary category theorem. Just recall, suppose X is a complete metric space where X equal to n equal to 1 to infinity en, where each en is closed. Then at least one of the set en must have non-empty interior. I hope my all viewers have understood. And uniform boundness theorem is simple corollary of Boundary category theorem. Sequence of continuous linear map Tn is said to be pointwise bounded if for each x belongs to x there is a constant mx such that supremum n belongs to natural number mod Tnx less than equal to mx. This sequence of continuous function is true for each x belongs to x. For each x belongs to x, supremum of, if you consider x equal to 2, then and n equal to 1, then t1 2. Here n would be varies and 2 is fixed. And this sequence of continuous function is true for each x belongs to x. Then this sequence of continuous function is called as pointwise bounded. The sequence of continuous linear form Tn is uniformly bounded if there exists constant m such that supremum n belongs to natural number mod Tnx less than equal to m. This is true for all norm x less than equal to 1. Here, this is true for all x and for all n. Actually, this is true globally. And this is true, pointwise boundedness is true for each point. And in nonlinear space, the statement of the uniform boundedness theorem is, let X be a Banach space and Y be a norm space and F be the set of continuous linear operator from X to Y. Suppose for all x belongs to x, there exists mx such that all continuous linear operator belongs to f, then norm of tx less than equal to mx means this is the pointwise boundedness, because this is depends on point. Then there exists k greater than 0 such that all t belongs to set of continuous linear operator such that norm t less than equal to k. That means this result tells us family of continuous linear operator from a Banach space to any nonlinear space, pointwise boundedness always imply uniformly bounded. Banach space to norm space, then pointwise boundness imply always uniformly bounded. The proof is such type for each k belongs to n. Let ak be the set, this is true for all x, and ak is the set of those x in x such that norm tnx less than equal to k, and this is true for all n. And ak is, we claim ak is closed. ak is closed, that means x belongs to ak closure. So there exists sequence xj in ak who is converging to x. Since xj belongs to ak for every fixed n, then norm tn xj less than equal to k, and let j tends to infinity, then norm tnx would be less than equal to k, because norm is a continuous function and tn is continuous. Then since ak is the set of those x in x such that non tnx less than equal to k, for this is true for all n, that means x belongs to ak, and ak is closed. That means ak is closed for all k, and since norm tnx less than equal to cx, this is given. So, and this is true because this is the pointwise boundness. We have to prove uniformly boundness. Then for each x belongs to x belongs to some ak. Therefore x is a union of n equal to 1 to infinity ak, where ak is the closed set. I hope my all viewers have understood. Then since x is a complete, therefore by Baire category theorem, x is complete by Baire category theorem, some ak contain open ball. Consider this is b naught equal to b of x naught r, which is subset of ak naught, and consider x be an arbitrary point, and let z equal to x naught plus gamma x, where gamma equal to r by 2x naught. Here a ball x naught with radius r contain the point z. Because z equal to x naught plus gamma x, here the ball centered x naught radius r contain the point z, then norm of z minus x naught equal to gamma norm of x, and the value of gamma r by 2 norm of x times norm of x. This is equal to r by 2, who is less than r. That means z belongs to b naught. Since z minus x naught, norm of z minus x naught less than r, that means z belongs to an b naught, and b naught contain a k naught. Therefore, since z belongs to a k naught and a k equal to those x such that norm Tnx less than equal to k, therefore we can write norm Tnz less than equal to k naught, and this is true for all n. Therefore, norm Tn x naught less than equal to k naught. Since x naught is the center of b naught, therefore norm of Tn x equal to norm Tn x equal to 1 over gamma Tn z minus x naught, and this is equal to 1 over gamma norm Tnz plus norm Tn x naught. And gamma equal to r by 2 norm x naught, therefore 1 over gamma less than equal to 2 x naught over r since norm Tnz less than equal to k, therefore this is less than equal to k naught, this is less than equal to 2 k naught. Therefore this is less than equal to 4 by r norm x k naught. Therefore we can write supremum of norm x equal to 1 norm Tn x divided by norm x less than equal to 4 by r k naught, which is equal to, we can write c naught. That imply norm t less than equal to c naught. Therefore, given pointwise boundness, this imply uniformly bounded. And this is true for each n and for all x. Therefore, pointwise bounded imply uniformly bounded. I hope my all viewers have understood clearly. Okay. Well. Now I will see one example. Space of polynomial. The norm space X of all polynomial with norm defined by norm of x equal to maximum of mod alpha I, where this alpha naught, alpha 1 be the coefficient of x, and this space of polynomial is not complete. Why? We construct a sequence of bounded linear operator on x which satisfies norm Tnx less than equal to Cx. But there is no such C such that the sequence fnx satisfy norm Tn equal to norm of fn less than equal to C. This is true for all. That means the point-wise boundedness does not imply the uniformly boundedness. Therefore, x cannot be complete because point-wise boundedness imply uniformly boundedness. This is actually the use of Bailey category theorem. Bailey category theorem imply when x is complete. Here point-wise boundedness does not imply uniformly boundedness. Therefore, the given x cannot be complete when x is Banach space to norm-linear space, any norm-linear space, then always point-wise boundedness imply uniformly boundedness. Since this is point-wise bounded, not imply uniformly boundedness, that means x cannot be complete. Here we may write the polynomial of degree nx in the form xt equal to summation j equal to 0 to infinity alpha j to the power j, where alpha j equal to 0. This is true for all j belongs to nx. As a sequence of operator on x takes sequence of functions, we may write a polynomial x not equal to 0 of degree nx in the form xt equal to summation j equal to 0 to infinity alpha j t to the power j, where alpha j equal to 0 for j greater than n. As a sequence of operator on x, we take sequence of function Tn equal to Fn defined by Tn 0 equal to Fn 0 and Tnx equal to Fnx equal to alpha naught plus alpha 1 up to alpha n minus 1. Here Fn is linear and bounded. Since alpha j less than equal to norm x, so Fnx equal less than equal to n times norm x. Furthermore, for each x belongs to x, the sequence Fnx satisfies norm Tnx less than equal to Cx, because polynomial x of degree nx has nx plus 1 coefficients. and we have mod fn x less than equal to nx plus 1 max mod alpha z, which is equal to cx. We have to show the sequence mod fn x does not satisfy norm tnx less than equal to c. That means there is no such c such that the sequence mod fn x satisfy norm tn equal to norm fn less than equal to c, and this is true for all n. For this, we choose xt equal to 1 plus t square up to t to the power n, and norm x equal to max alpha I, which is equal to 1, and fn x equal to 1 plus 1 up to 1. This is n times, that means this is n, which is equal to n norm of x. Defined fn x is the coefficient of alpha 0 plus alpha 1 up to alpha n minus 1. So fn x is 1 plus up to 1, this is equal to n, which is n times norm of x. Therefore, norm of fn x greater than equal to absolute value of fn x divided by norm of x, which is equal to n. Therefore, norm fn is unbounded. I hope my all viewers have understood. Okay, well. But there is no such c such that the sequence fn x satisfy norm tn equal to norm of fn less than equal to c. This is true for all n.